Picture this. Right now, at this very moment, something is heading toward us from the depths of space. Its name is C₂-dominated G3 Atlas, and according to every official calculation, every press briefing, every carefully constructed model, it's going to miss us. The numbers say we're safe, the trajectories look clean, the distance at closest approach, far enough that you could line up multiple Earths between us and still have room to spare. But here's what keeps me staring at my screen late at night, what makes my hands shake just slightly when I pull up the latest observation data. Comets lie. Not intentionally, of course. They don't have consciousness or malice, but they do something far more unsettling. They change. They evolve. They deviate from the mathematical certainty we desperately try to impose on them. Tonight, we're going deep into the shadows of what the agencies won't discuss in their public statements. We're exploring the scenarios that exist in the margins of error bars, in the gaps between observation windows, in the uncomfortable silences during scientific conferences when someone asks, "But what if?" Before we begin this journey together, I need you to do something. If this investigation resonates with you, if you feel that same unsettling curiosity that drove me to spend months researching this, hit that subscribe button. Drop a comment telling me where you're watching from and what time it is in your part of the world. Because what we're about to uncover isn't just about one comet, it's about how we understand risk itself in an unpredictable universe. And trust me, by the time we reach the end, you'll see C₂-dominated G3 Atlas very differently than you do right now. Let's start with the comforting part, shall we? The part that lets everyone sleep soundly at night. C₂-dominated G3 Atlas, when it reaches its closest point to Earth, will be millions upon millions of kilometers away. We're talking about distances so vast that light itself takes meaningful amounts of time to cross them. NASA's Jet Propulsion Laboratory has run the calculations thousands of times. The European Space Agency has independently verified the trajectory. Every major observatory on the planet has contributed data points, and they all agree, no impact, no collision, no catastrophe. The comet will sweep through our cosmic neighborhood like a ship passing in the night, close enough to observe, far enough to be harmless. Except, what does far enough really mean? Distance in space is a peculiar thing. We measure it in astronomical units, in millions of kilometers, in numbers so large they become abstractions. But distance alone tells us nothing about influence. It tells us nothing about the cone of uncertainty that surrounds every trajectory calculation. It tells us nothing about the forces we cannot directly measure, the behaviors we cannot predict, the changes happening in real time that won't show up in our models until it's too late to matter. Let me walk you through something that doesn't make it into the press releases. When astronomers say they've refined the trajectory of C₂-dominated G3 Atlas, what they mean is they've narrowed the uncertainty envelope. Think of it like this. Imagine you're trying to predict where a car will be in exactly 1 hour. If you know its current position and speed, you can make a prediction. But that prediction has error bars. The car might speed up, slow down, take an unexpected turn. Now imagine that car is actually a comet, millions of kilometers away, moving at tens of kilometers per second, venting gases you can't directly see, possibly shedding fragments too small or too dark to detect, spinning in ways that might be changing over time due to forces we can only infer from secondary effects. Suddenly, those error bars aren't so small anymore. The agencies have reduced the uncertainty by implementing better observation techniques, incorporating data from multiple instruments, running more sophisticated simulations. But reduced uncertainty is not the same as eliminated uncertainty. There's still a range of possible trajectories that C₂-dominated G3 Atlas could follow, and while the center of that range, the nominal trajectory, is indeed safe, the edges extend into territory that's less comfortable. How far do those edges extend? That's the question nobody seems eager to answer publicly. Here's what we know from the observation record. C₂-dominated G3 Atlas is not behaving like a simple inert rock following a predictable gravitational path. It's showing what scientists call non-gravitational acceleration. Something is pushing on this object besides gravity. That something is almost certainly outgassing. Frozen materials on the comet's surface warming up as it approaches the sun, turning directly from solid to gas and jetting away into space. These jets are invisible to casual observation, but they act like tiny rocket engines, and like rocket engines, they push. they steer, they change velocities in ways that pure gravitational calculations cannot predict. Now, the scientific community will correctly point out that they've incorporated these non-gravitational effects into their models. They'll show you elegant equations that account for the expected magnitude and direction of these forces. They'll demonstrate that even with outgassing, the trajectory remains well constrained within safe parameters, and I believe them. I believe they've done excellent work with the data they have. But here's the uncomfortable truth. Those models make assumptions. They assume the outgassing will continue at relatively predictable rates. They assume the jets will fire in directions that can be inferred from observed brightness patterns and tail structures. They assume the comet's structure is relatively uniform, without hidden vents or weak spots that might suddenly give way under thermal stress. What happens when an assumption breaks? There's a concept in risk analysis called black swan, events, occurrences that are so far outside our normal expectations that we fail to plan for them, even though in retrospect they seem obvious. The financial crisis of 2008 was a black swan. September 11th was a black swan. These weren't unimaginable events, they were simply unmodelled events. Could C₂-24 G3 Atlas harbour its own black swan? A sudden major outgassing event that dramatically changes its velocity? A structural failure that creates fragments on divergent paths? An interaction with interplanetary dust or plasma that produces effects we haven't accounted for? The distance that seems so comfortingly large right now is measured against our current understanding. But if that understanding is incomplete, if there are forces or behaviours we haven't properly characterised, then the distance becomes less of a guarantee and more of a hopeful estimate. Let me share something that didn't get much attention in the mainstream coverage. During preliminary observations of C₂-24 G3 Atlas, several amateur astronomers reported peculiar fluctuations in brightness that didn't match the expected pattern for a comet at that distance and activity level. These reports were largely dismissed as observational artifacts, noise in the data, atmospheric interference, equipment limitations. But what if they weren't artifacts? What if the comet was already showing signs of unusual behaviour and we collectively chose to interpret the data in the most comfortable way? I'm not suggesting a conspiracy. I'm suggesting something far more human: cognitive bias. When you're tracking an object that you've already calculated to be safe, there's a natural tendency to interpret ambiguous data in ways that confirm that safety. Anomalies become artifacts. Uncertainties become rounding errors. Edge cases become theoretical exercises, until they're not. The mathematical models we use to predict cometary trajectories are magnificent achievements of human intellect. They incorporate Newtonian mechanics, relativistic corrections, sophisticated outgassing models, and centuries of observational experience. But they're still models. They're simplified representations of reality, and reality has a disturbing habit of being more complex than our representations. Every model has boundaries, conditions beyond which it stops being accurate. For cometary trajectory prediction, those boundaries include assumptions about structural integrity, composition, outgassing behaviour, and the absence of unexpected external forces. C₂-24 G3 Atlas is testing some of those boundaries. Its composition appears unusual based on spectroscopic analysis. Its outgassing pattern doesn't quite match the standard templates. Its response to solar heating has shown slight deviations from predicted behaviour. Nothing dramatic, nothing that screams danger, but enough to make careful observers pause and wonder. In science, when your observations don't quite match your models, you have two choices. You can adjust your interpretation of the observations to fit the models, or you can adjust your models to fit the observations. Both approaches are valid in different circumstances. But there's a third option that's less discussed. You can acknowledge that your models might be fundamentally inadequate for this particular object, and you can admit that your uncertainty is larger than you'd like it to be. That third option doesn't make for reassuring press conferences, so we're left with a paradox. The distance is real, millions of kilometres of empty space between us and C₂-24 G3 Atlas. The calculations are real, performed by brilliant scientists using sophisticated tools. The conclusion seems inescapable: we're safe. And yet the uncertainty is also real. The unknowns are real. The possibility that this object might behave in ways we haven't fully anticipated is very, very real. Distance provides protection against the known, but it provides far less protection against the unknown. Now let's talk about what C₂-24 Atlas is actually made of, because this is where things get genuinely weird. When most people think of comets, they picture dirty snowballs, chunks of ice mixed with rock and dust, leftovers from the formation of our solar system. That's not entirely wrong for typical comets that have spent billions of years in stable orbits within our sun's domain. We know what to expect from those objects: water ice as the primary volatile component, some frozen carbon dioxide and carbon monoxide, various organic compounds, and a rocky dusty matrix holding it all together. C₂-24 Atlas doesn't follow that script. Spectroscopic observations have revealed something genuinely unusual. This comet's emissions are dominated not by water vapour, but by carbon dioxide. And I don't mean slightly more CO₂ than typical, I mean dramatically, overwhelmingly more. The ratio of carbon dioxide to water in the coma has been measured at levels that place this object in a category, almost by itself among known comets. Why does this matter? Because different ices sublimate at different temperatures. Water ice needs significant solar heating before it starts turning to vapour in meaningful quantities. Carbon dioxide, on the other hand, is much more volatile. It starts sublimating at much greater distances from the Sun, at much lower temperatures. This means C₂-24 Atlas has likely been outgassing longer and more vigorously than models based on water ice-dominated comets would predict. It means the forces pushing on this object, those non-gravitational accelerations we discussed earlier, could be stronger and more persistent than standard assumptions would suggest. It also means the behaviour of this comet as it continues its trajectory could be fundamentally different from what we've learned to expect. But the strangeness doesn't stop at composition. There's something else, something that suggests this object has a history unlike anything in our solar system. The outer layers of C₂-24 Atlas appear to have been processed by something called galactic cosmic rays. These are high-energy particles that pervade the space between stars, protons, atomic nuclei, even the occasional electron, all accelerated to nearly the speed of light by supernova explosions, neutron stars, and other violent cosmic phenomena. For an object to show significant cosmic ray processing, it needs to have been exposed to interstellar space for a very, very long time. We're talking millions of years at minimum, possibly tens of millions or more. During all that time, these energetic particles have been slowly but steadily altering the chemical makeup of the comet's surface. Analysis suggests that this irradiation has created a crust, a layer of processed material that could extend perhaps 20 or 30 meters deep. This crust is enriched in carbon dioxide, created from the breakdown of carbon monoxide by cosmic rays, contains complex organic molecules that don't exist naturally in our solar system, and has physical properties that are genuinely unknown. We've never studied this kind of material before. We don't know how strong it is, how it responds to thermal stress, how it fractures, or how it regulates the flow of gases from deeper layers below. This is not idle speculation about alien technology, or anything so dramatic. This is straightforward physics. An object that has been wandering between the stars for eons will have surface properties fundamentally different from objects that formed and remained within our solar system. The chemistry is different. The structure is different. The behaviour under solar heating will be different. And here's the unsettling part. When you're trying to predict how an object will behave, you need to know its material properties. You need to know how it responds to stress, how it conducts heat, how strong its internal structure is, how gases move through its interior. For C₂-24 Atlas, we're essentially guessing, educated guessing to be sure, sophisticated guessing based on decades of cometary science, but guessing nonetheless, because we've never actually studied this kind of material up close. Recent polarimetric observations, studies of how light scatters off particles in the comet's coma, have revealed another anomaly. The way dust particles from this comet interact with light is unlike anything seen from solar system comets. The polarization signature is so distinct that it has researchers genuinely puzzled about what the dust grains must look like at the microscopic level. Are they more angular, more porous? Do they have unusual coatings created by millions of years of cosmic ray bombardment? Are they aggregates of smaller particles bonded in unfamiliar ways? We don't know. And without knowing, we can't accurately predict how those particles will behave when they're ejected from the nucleus, how they'll interact with solar radiation, or where they'll end up as the comet continues its journey. There's also the question of what lies beneath that irradiated crust. The cosmic rays can only penetrate so deep. Below 20 or 30 meters, there should be pristine material, ice and rock that has remained essentially unchanged since this object formed around another star, in another part of the galaxy, perhaps billions of years ago. What happens when the sun's heat finally penetrates through that protective crust? What happens when gases trapped beneath it start to build up pressure? What happens if that crust suddenly fractures? The honest answer is, we don't fully know. Comets are fragile objects. We've watched them break apart before, sometimes spectacularly. Comet Shoemaker-Levy 9 shattered into dozens of pieces before plunging into Jupiter. Comet Linear disintegrated as it approached the Sun, creating a spectacular debris cloud. Comet Schwarzmann-Wachmann 3 split into multiple fragments that slowly drifted apart. These fragmentations happen for various reasons: thermal stress, tidal forces from nearby massive bodies, rotational instability, or simply structural weaknesses giving way under the stresses of outgassing. C₂-24 G3 Atlas has an unusual structure, a cosmic ray-processed crust over a volatile-rich interior, with material properties we don't fully understand. If there was ever a comet that might behave unpredictably, this would be it. And unpredictability, in the context of trajectory prediction, is deeply concerning. Imagine if a significant chunk of the nucleus were to break away. That fragment would have its own trajectory, slightly different from the parent body. It would have its own outgassing pattern, creating its own non-gravitational forces, and because it's a fragment, smaller, darker, potentially composed of material that's hard to detect, we might not even spot it immediately. Days or weeks could pass before anyone realized that C₂-24 G3 Atlas was no longer a single object, but had become 2, or 3, or a dozen pieces, each following its own path, each with its own uncertain trajectory. This isn't fear-mongering. This is acknowledging that comets with unusual compositions and structures can behave in unusual ways. The chemical strangeness of C₂-24 G3 Atlas matters because chemistry drives behavior. The CO₂ dominance means stronger, more persistent outgassing. The cosmic ray-processed crust means unknown structural properties. The polarimetrically unusual dust means we don't fully understand the material being shed into space. And all of this uncertainty compounds when you're trying to predict where this object will be weeks or months from now. The agencies base their trajectory calculations on the best available models, but those models assume certain material behaviors: how ice sublimates, how crust responds to heating, how fragments, if any, will behave. When the actual object deviates from those assumptions, even slightly, the predictions become less reliable. So yes, the chemistry of C₂-24 G3 Atlas is strange. Genuinely, measurably, scientifically strange. And that strangeness translates directly into uncertainty about its future behavior. In the next section, we'll explore what happens when observations don't match predictions, when the data coming back from our telescopes shows things that don't quite fit the models, because that's exactly what's been happening with this comet, and it's what convinced me that this story needed to be told. Let me tell you about the thing that originally drew me down this rabbit hole, the detail that transformed C₂-24 G3 Atlas from just another comet into something that demands closer scrutiny. It started with images, not dramatic Hollywood-style images of a blazing comet filling the sky, but subtle technical images captured by professional observatories and importantly by skilled amateur astronomers around the world. These images showed something odd about the comet's tail and coma, the cloud of gas and dust surrounding the nucleus. In a typical comet, the tail points reliably away from the sun, pushed by solar wind and radiation pressure. The coma tends to be fairly symmetric, perhaps elongated slightly in the direction away from the sun. C₂-24 G3 Atlas, at various points in its observation history, didn't quite follow this pattern. Multiple observers noted that the coma seemed to have structure, not just a uniform glow, but distinct regions of brightness and darkness that didn't align with simple models of gas and dust distribution. The tail occasionally showed what appeared to be multiple filaments, suggesting complex outgassing from different regions of the nucleus. Most peculiarly, there were several reports of what looked like material oriented toward the sun, an anti-tail in the terminology of comet observers. This shouldn't exist according to standard physics. Radiation and solar wind push material away from the sun, not toward it. Now, anti-tails aren't completely unheard of. They're typically optical illusions created by geometry. When you're viewing a comet from just the right angle, material that's actually moving away from the sun can appear to point toward it due to perspective effects. But the anti-tail features observed in CO₂-24 G3 Atlas appeared in multiple observations from different viewing angles. That shouldn't happen if it's purely a geometric effect. The standard explanation offered was that these structures were caused by localized jets, specific vents on the nucleus firing in particular directions as the comet rotated. This is plausible. It's certainly the most conventional explanation. It doesn't require any exotic physics or unusual assumptions. But here's what bothers me. The pattern of these jets, if that's what they are, doesn't quite match what we'd expect even from asymmetric outgassing. Computer models of rotating, venting comet nuclei produce certain signature patterns in the coma and tail. The observations of CO₂-24 G3 Atlas showed features that were similar but not quite right. It's like looking at a face and realizing something is slightly off. The eyes aren't quite symmetrical, or the proportions don't match what you expect. Nothing is dramatically wrong, but your brain keeps sending up little warning flags. Professional astronomers notice these discrepancies too. I've read through observation reports and scientific papers, and there's a subtle but persistent theme. Unexpectedly, anomalous, requiring further investigation. These are the phrases scientists use when they're trying to maintain professional objectivity while saying, "This doesn't make complete sense." Then came the brightness variations. Comets brighten and dim as they approach and recede from the sun. That's completely expected. But CO₂-24 G3 Atlas showed brightness fluctuations that didn't match the smooth curves predicted by models. There were sudden upticks, unexpected plateaus, and periods where the brightness changed more rapidly or more slowly than thermal models suggested it should. Again, the standard explanations were offered: changing viewing geometry, variable dust production, rotational effects bringing different surface regions into view. All plausible, all reasonable, but all requiring multiple adjustable parameters to make the models fit the data. And in science, when you need to keep adjusting your model to match observations, it often means your fundamental assumptions might be wrong. What really caught my attention was the timing of some of these anomalies. They occurred during periods when multiple professional observatories and capable amateur astronomers were all watching. This wasn't a case of a single questionable observation that could be dismissed as an artifact. Multiple independent observers, using different equipment from different locations, were all seeing behaviours that didn't quite match predictions. And here's where things get genuinely concerning from a trajectory prediction standpoint. If we don't fully understand what's happening with the comet's outgassing, if those brightness variations and structural features represent processes we're not correctly modelling, then our predictions about the non-gravitational forces acting on this object might be wrong. Remember, those non-gravitational forces are what's pushing the comet away from a purely gravitational trajectory. If they're stronger than we think, acting in different directions than we assume, or varying in ways we haven't accounted for, then the trajectory predictions become less reliable. It's not that the scientists are doing bad work, it's that they're working with incomplete information about an object that's genuinely unusual. There's also a more subtle problem: data delays and processing backlogs. When an observatory captures an image of CO₂-24 G3 Atlas, that image doesn't instantly become available for analysis. It needs to be downloaded, calibrated, processed, analysed, and only then can it contribute to our understanding. This process can take days, sometimes weeks, especially for data from space-based observatories or instruments that are juggling multiple observation programs. During those delays, the comet continues moving, evolving, potentially changing in ways we won't know about until the delayed data finally gets processed. Imagine you're trying to predict where a hurricane will go, but your weather data is always a week old. You might be making predictions based on conditions that no longer exist. The hurricane might have intensified, changed course, or developed new behaviour patterns, and you wouldn't know until your delayed observations finally arrived. That's approximately the situation with detailed observations of CO₂-24 G3 Atlas. We're always somewhat behind, always reconstructing past behaviour and hoping it remains predictive of future behaviour. For a typical, well-understood solar system comet, this delay doesn't matter much. Their behavior is predictable enough that a week-old observation still tells you what you need to know, but for an object showing anomalous features, for a comet that's not quite following the standard playbook, those delays become significant blind spots. I've spoken informally with observers who've mentioned frustration about this lag. They see something interesting in real-time observations, something that might be important, but by the time the data is properly processed and published, the comet has moved on. The opportunity to do immediate follow-up observations to catch the comet in the act of whatever it was doing has passed. This creates a knowledge gap, a window of time during which we simply don't know with high confidence what the comet is doing. And if significant changes happen during those windows, if structural events or major outgassing episodes occur when we're not watching or when our data is sitting in a processing queue, we might miss them entirely. The implications for trajectory prediction are obvious. If the comet undergoes a significant change, a major jet activates, a chunk breaks off, the rotation rate shifts. During one of these observational gaps, our models won't know about it until much later. By then, the effect on trajectory might already be significant. This isn't about conspiracy or cover-up. It's about the practical limitations of doing astronomy on a tight budget with limited resources. Telescopes are oversubscribed. Data processing takes time. Follow-up observations require planning and approvals. The system simply wasn't designed for the kind of rapid, continuous monitoring that unusual objects like C20-C24, G3 Atlas might actually require. And so we're left with a situation where the observations we do have show subtle but persistent anomalies, where our understanding of the comet's behavior is incomplete, where data delays create blind spots, and where all of this uncertainty feeds directly into the reliability of trajectory predictions. The distance might be large, the nominal trajectory might be safe, but nominal assumes we understand what the comet is doing, and the observations suggest our understanding is incomplete. Now we need to talk about motion, not the simple, elegant elliptical orbits that make celestial mechanics beautiful, but the messy, complex, hard-to-predict motion that happens when a comet is venting gases, possibly fragmenting, and responding to forces that are difficult to measure from millions of kilometers away. Here's the central problem. Predicting a comet's trajectory requires knowing all the forces acting on it. Gravity is easy. We understand that beautifully, and we can calculate gravitational interactions with exquisite precision. But comets don't move under gravity alone. Every kilogram of gas and dust that jets away from a comet's nucleus carries momentum. By conservation of momentum, when that material flies off in one direction, the nucleus gets pushed in the opposite direction. If this venting is symmetric, roughly equal in all directions, the pushes average out, and the net effect is minimal. But if it's asymmetric, if certain regions are venting more strongly than others, or if the comet's rotation brings active vents into and out of sunlight in a way that creates a persistent thrust in one direction, then you get a real, measurable change in the comet's trajectory. This is what scientists call non-gravitational acceleration, and it's genuinely difficult to model accurately. Why? Because you need to know the rate of mass loss, the velocity of the escaping gas, the direction of the jets, how all of these change as the comet rotates, how they respond to changing solar heating, whether new vents might suddenly open, whether existing vents might shut down or shift position due to structural changes. For a well-studied solar system comet that's been observed over multiple orbits, you can calibrate these parameters empirically. You can see how the comet behaved in the past and use that to predict how it will behave in the future. For C2024 G3 Atlas, we don't have that luxury. This is our first observation of this object. We don't know its history. We don't know if its current outgassing pattern is typical for it or unusual. We don't know if it's structurally stable or on the verge of fragmenting. We're making educated guesses based on general comet behavior, but this comet, with its unusual composition, its cosmic ray-processed crust, its anomalous observational features, might not follow general behavior patterns. Let's talk numbers for a moment, because I think it's important to understand the scales involved. A typical active comet might be losing mass at rates anywhere from tens to hundreds of kilograms per second when it's near the Sun. The gas escaping the nucleus is moving at speeds of several hundred meters per second, faster than the speed of sound on Earth. Now the comet's nucleus itself masses billions or trillions of kilograms, so the force from outgassing seems tiny by comparison, but it's continuous, It acts for hours, days, weeks as the comet approaches, passes, and recedes from the Sun. When you integrate that tiny force over extended periods, the velocity change accumulates. Over weeks, you might see changes of meters per second. Over months, tens of meters per second. That translates into positional changes of thousands or even millions of kilometers over the course of the comet's trajectory through the inner solar system. Millions of kilometers might still sound like nothing compared to the vast distances involved. But remember, we're talking about deviations from predicted trajectory. If the nominal path passes at, say, 200 million kilometers, but non-gravitational forces could shift that by several million kilometers in an uncertain direction, suddenly the error bars start to matter, especially if some of those uncertain trajectories trend inward. Now, here's where it gets even more complex. The outgassing is almost certainly not constant. As the comet rotates, an observation suggests C₂-dominated G3 Atlas has a rotation period of roughly 15 to 17 hours. Different parts of the surface get exposed to sunlight. Active regions heat up and vent strongly when they're facing the sun, then cool and quiet down when they rotate into darkness. This creates a periodic, pulsing thrust pattern. Sometimes the thrust points in one direction, sometimes in another, depending on where the active vents are located on the nucleus and which way they're pointing at any given moment. Modelling this requires knowing the rotation axis, the rotation rate, which might be changing due to the outgassing itself, the locations of active regions, and how the activity level of each region responds to solar heating. In practice, scientists use simplified models. They estimate an average thrust direction and magnitude that hopefully captures the bulk behavior even if the detailed moment-to-moment forces are much more complex. These simplified models work reasonably well for typical comets. But are they adequate for C₂-dominated G3 Atlas? The anomalous tail structures and brightness variations suggest that this comet's outgassing might be more complex, more variable, more structured than the simplified models assume. If so, the trajectory predictions could be correspondingly less accurate. There's another dynamic that's rarely discussed in public communications: the possibility of sudden outbursts. Comets occasionally undergo dramatic, sudden increases in activity, brightening by factors of 10 or even 100 over the course of hours or days. These outbursts are thought to be caused by sudden exposure of fresh ice, perhaps due to a landslide or collapse of surface material, sudden opening of a new vent, or perhaps the explosive release of gas that had been trapped beneath the surface. When an outburst happens, it temporarily but dramatically increases the thrust on the nucleus. If the outburst is directional, coming from a specific region rather than uniformly across the surface, it can give the comet a significant velocity kick in an unexpected direction. Has C₂-dominated G3 Atlas shown any signs of outburst activity? The brightness variations I mentioned earlier could potentially be interpreted that way, though they're not as dramatic as the most famous comet outbursts on record. Still, even a modest outburst, if it occurs at the right time and in the right direction, could measurably affect the trajectory. The problem is that outbursts are inherently unpredictable. We don't have a good physical model that lets us say, this comet will definitely experience an outburst on this date. We can sometimes see that a comet is prone to outbursts based on past behavior, but for a first-time visitor like C₂-dominated G3 Atlas, we simply don't know. There's also the fragmentation scenario we touched on earlier. If the nucleus breaks apart, whether through thermal stress, structural weakness, or rotational instability, each resulting fragment becomes its own trajectory prediction problem. Fragments can have very different properties from the parent nucleus. They might be more volatile, if they're made of relatively pure ice, or more inert, if they're mostly rock. They might spin differently, vent differently, and therefore accelerate differently. Tracking and predicting the behavior of multiple fragments, each with its own uncertain properties, is a nightmare scenario for trajectory calculation. And here's the thing, we might not even realize fragmentation has occurred until well after the fact. Fragments stay relatively close together initially, so from Earth they might look like a single elongated object. It could take days or weeks before the fragments separate enough to be resolved as distinct objects. During that time, we'd be trying to model the trajectory assuming a single body, when in reality we're dealing with multiple bodies, each responding differently to solar heating and outgassing. All of these dynamic complexities, asymmetric outgassing, rotation effects, possible outbursts, potential fragmentation, exist in a regime where our measurements are uncertain and our models are simplified. The agencies aren't being dishonest when they say the trajectory is well constrained. Given the models they're using and the observations they have, their calculations are probably quite good. But the key questions are the models adequate for this particular comet? Are the observations complete enough? Are there dynamic effects happening that we're not fully capturing? And here's the really uncomfortable part. We won't know for certain until the comet has passed. Only after the fact, only once we can look back at the complete observational record and compare it to what actually happened, will we know whether our models were accurate. By then, of course, it won't matter for this encounter, but it will matter for our confidence in predicting the next unusual comet, the next unexpected visitor, the next object that doesn't quite follow the standard playbook. CO₂-24 G3 Atlas is, in a very real sense, a test case. It's testing whether our methods for trajectory prediction, refined over decades of observing typical solar system comets, are robust enough to handle something unusual, something with strange chemistry, anomalous behavior, and limited observational history. I hope they are. I genuinely do. But hope isn't the same as certainty, and the dynamics of this comet introduce uncertainties that are difficult to fully quantify. Let's shift our thinking for a moment. Suppose, just suppose, that CO₂-24 G3 Atlas does indeed pass at a safe distance, exactly as predicted. No impact, no near miss, no last-minute surprises. The agencies were right, the models were adequate, and the comet sweeps past us and continues on its way. Are we out of the woods? Not necessarily, because a comet doesn't travel alone. It travels with an entourage of debris, dust, pebbles, possibly larger fragments, trailing behind it and alongside it, spreading out into an elongated cloud that follows the comet's general orbital path. This debris cloud can persist for years, decades, even centuries after the parent comet has moved on, and if that cloud intersects Earth's orbit at some point, we could find ourselves encountering material from CO₂-24 G3 Atlas long after the comet itself is gone. This is not speculation. This is exactly how meteor showers work. The Perseids, the Leonids, the Geminids, all are debris streams from comets, or in some cases, asteroids acting like comets. Earth plows through these streams once a year, and we see the resulting meteors as particles burn up in our atmosphere. For well-established meteor showers from known parent bodies, this is a beautiful, harmless phenomenon. But what about a new debris stream from an unusual comet? Here's what makes the CO₂-24 G3 Atlas debris feel potentially concerning. We don't know what it's made of. The unusual composition of the comet, carbon dioxide dominated, cosmic ray processed, with polarimetrically strange dust, means the debris it sheds will have unfamiliar properties. The particles might be unusually fragile or unusually hard. They might ablate differently in Earth's atmosphere. They might carry unusual chemistry. More importantly, the relative velocity is likely to be high. CO₂-24 G3 Atlas is moving through the solar system at speeds typical of objects that originated beyond Neptune, possibly even from the interstellar region. If Earth intersects its debris stream, particles would hit our atmosphere at extreme velocities, potentially faster than any meteor shower we currently experience. High-velocity impacts mean more energetic ablation, brighter meteors, potentially more danger to satellites in low Earth orbit. A satellite collision with even a small particle at these speeds could be catastrophic. Now, let me be clear, this is not an immediate threat. Even if CO₂-24 G3 Atlas leaves behind a debris stream, and even if that stream eventually crosses Earth's orbit, it would take years or decades for the material to drift into position. This isn't something that's going to happen next month or even next year, but it is something that could affect our space infrastructure decades from now, and it's something we should be thinking about now, while we have the chance to study the comet and characterize what kind of debris it's producing. There's also a more subtle effect to consider: gravitational stirring. As CO₂-24 G3 Atlas moves through the solar system, particularly if it passes through or near regions populated by small bodies like the asteroid belt, its gravitational influence, tiny though it is for a single small object, gets amplified by collective effects. Think of it this way. The comet doesn't need to directly hit an asteroid to affect it. It just needs to pass close enough that the asteroid's orbit gets slightly perturbed. Velocity changes by a few meters per second, orbital period shifts by a few days, eccentricity increases by a tiny fraction. By themselves, these perturbations are negligible. But here's the key insight: small changes in orbital parameters can compound over time. An asteroid that gets a slight nudge from the comet might, over years or decades, gradually migrate into a new orbital resonance with Jupiter or Saturn. Those resonances can amplify the effect, causing the asteroid's orbit to evolve significantly. Eventually, some of these stirred asteroids might find themselves on Earth-crossing orbits, not because the comet directly put them there, but because the comet initiated a cascade of gravitational interactions that, over long time scales, reshaped the orbital distribution of small bodies. This is an incredibly subtle effect, and it's extraordinarily difficult to model because you need to track thousands of potential interactions over decades or centuries. But it's physically real, and for an unusual object passing through the inner solar system, it's a potential long-term influence that could matter. I want to emphasize, this is not the same as saying C₂-dominated is going to cause an asteroid impact decades from now. The probabilities are low, the effects are subtle, and there are many other factors that influence asteroid orbits. But it does mean that the influence of this comet extends beyond its immediate flyby. It's leaving marks on the solar system, in the form of shed debris, in the form of subtle gravitational perturbations that will persist and potentially evolve in ways we won't fully understand for years. This is what I mean when I say distance isn't everything. The comet can pass at a safe distance and still have lingering effects that matter. There's also the possibility of chemical contamination, and I use that word in the scientific sense, not the pejorative sense. C₂-G3 is carrying material from another stellar environment, material that has been processed by radiation fields we've never directly studied, material with chemical signatures that don't match anything native to our solar system. When this material gets shed into space, and eventually, potentially, intersects Earth's atmosphere or orbital environment, it introduces a new chemical component. In tiny trace amounts, this doesn't matter at all, but over years, if the debris stream is persistent and we're continuously encountering it, trace amounts add up. Could this affect Earth's upper atmosphere? Could it introduce new dust populations in near-Earth space that change the thermal or radiation environment that satellites experience? Could it seed chemical reactions we haven't anticipated? Again, these are subtle, long-term considerations, not immediate threats. But they're worth thinking about, because they represent ways that an interstellar visitor can influence our local environment without ever coming close to impacting us directly. The agencies focus on collision probability because that's the clear, immediate, calculable risk. But influence probability, the chance that this object will leave behind effects that matter over longer timescales, is much harder to assess and much less discussed. C₂-G3 is potentially introducing interstellar debris into our solar system, perturbing the orbits of small bodies in subtle ways and seeding chemical changes in near-Earth space. None of these effects are catastrophic, none are immediate, but collectively they represent a kind of contamination of our local cosmic environment. And here's the final, unsettling thought. We're not monitoring for these effects. Our planetary defense systems are focused on finding and tracking objects that might hit us in the foreseeable future. We're not systematically looking for debris streams that might matter decades from now. We're not carefully tracking subtle orbital changes in asteroid populations that might trace back to gravitational stirring. We're not monitoring for chemical changes in near-Earth space that might have interstellar origins, so even if these effects are real and significant, we might not notice them until much later, until they've already become embedded in the system. The debris field scenario isn't about impact, it's about influence. An influence spread over decades, diffused across millions of kilometers, expressed through chains of subtle interactions, is much harder to track and predict than a simple collision. This is why I keep coming back to the inadequacy of focusing solely on distance and immediate collision probability. C₂-G3 is a systemic perturbation, not just a point mass following a ballistic trajectory. It's interacting with our solar system in multiple ways, on multiple timescales, through multiple mechanisms, and we're only beginning to think seriously about what that might mean. Let me now address something that's been gnawing at me throughout this investigation: the gaps in our ability to continuously monitor objects like C2024 G3-ATLAS. Our astronomical infrastructure, impressive as it is, was not designed for real-time, continuous tracking of rapidly evolving threats. Most telescopes operate on scheduled observation programs where time is allocated months in advance. Getting emergency observing time requires justification, approvals, and often involves bumping other important science. For C2024 G3-ATLAS, this means there are periods, sometimes days at a time, when nobody is actively observing it with high-quality instruments. During those gaps, the comet continues evolving, outgassing, potentially changing, and we're flying blind. Amateur astronomers help fill some of these gaps, and their contributions are genuinely valuable. But amateur equipment, while increasingly sophisticated, typically lacks the light-gathering power and spectroscopic capabilities needed to detect subtle changes in comet behavior. What we desperately need, is a network of dedicated monitoring telescopes whose sole purpose is to watch potentially interesting objects continuously, not just when there's a scheduled observation window, but constantly, building up a complete record of behavior that would let us spot changes as they happen, rather than reconstructing them after the fact from scattered observations. This kind of monitoring network doesn't exist yet, at least not for comets. We have systems like the Catalina Sky Survey and Pan-STARRS that search for new near-Earth objects, but they're optimized for discovery, not for detailed, continuous monitoring of known objects. The monitoring gap means that when we see something unusual in one observation, say an unexpected brightness spike or a new structural feature in the tail, we often can't immediately follow up to see what happens next. By the time the next scheduled observation comes around, hours or days later, the feature might have evolved or disappeared, and we've lost the chance to study it in detail. For C2024 G3-ATLAS, this has been frustrating for professional and amateur observers alike. They see tantalizing hints of interesting behavior, but can't study it continuously enough to really understand what's happening. And from a trajectory prediction standpoint, this is problematic. Those brief glimpses of unusual behavior might be telling us something important about forces acting on the comet, but without continuous monitoring, we can't properly characterize those forces or incorporate them into predictive models. To understand why C2024 G3-ATLAS matters, it helps to look at the history of how we've handled unusual comet encounters in the past. Consider comet Shoemaker-Levy 9, which I mentioned earlier. When it was discovered in 1993, already broken into multiple fragments, the immediate question was, where are these pieces going? Initial calculations showed they were on a collision course with Jupiter, an extraordinary prediction that turned out to be absolutely correct when the impacts occurred in July 1994. But here's the thing, Shoemaker-Levy 9 was relatively straightforward to model. The fragments were large enough to track individually, their trajectories were primarily governed by Jupiter's gravity, which we understand perfectly, and most importantly we had months of lead time to refine the predictions. C2024 G3-ATLAS presents a different kind of challenge. It's not fragments yet. It's not primarily governed by one dominant gravitational source, and its behavior is complicated by significant non-gravitational forces we don't fully understand. Or consider Oumuamua, the first confirmed interstellar object detected passing through our solar system in 2017. Oumuamua also showed non-gravitational acceleration, which sparked all kinds of speculation about its nature. Eventually, most scientists settled on, it's probably outgassing even though we don't see a coma. But the uncertainty was real, and the object's trajectory did deviate measurably from pure gravitational motion. C2024 G3-ATLAS is like Oumuamua's cousin, potentially from beyond our solar system, definitely unusual in composition and behavior, and definitely showing non-gravitational effects. But unlike Oumuamua, which passed through quickly and never came particularly close to Earth, C2024 G3-ATLAS is approaching us more directly. The historical lesson is that unusual comets often surprise us. Our models, calibrated on typical objects, don't always handle outliers well. And when an object is both unusual and coming relatively close, that's when we need to be most careful about overconfidence in our predictions. This entire discussion raises uncomfortable questions about how we approach planetary defense and risk assessment. Currently, our planetary defense infrastructure focuses almost entirely on impact probability. We search for near-Earth objects, we track their orbits, we calculate the chance they might hit us over the next century. If that probability is sufficiently low, the object is classified as no threat, and attention moves elsewhere. This makes sense for typical asteroids, which are inert objects following predictable gravitational trajectories, but it's inadequate for active comets, especially unusual ones that are showing behaviours we don't fully understand. C₂-dominated Atlas has a calculated impact probability of essentially 0 based on current models. By the standard criteria, it's no threat. But as we've explored throughout this investigation, there are many ways an object can matter beyond direct impact. Should we be expanding the definition of threat to include long-term debris field concerns? Should we be more actively monitoring objects with unusual properties, even if their immediate impact probability is low? Should we be investing in capabilities to respond to comets that might change behavior unexpectedly? These are policy questions, not just scientific ones. They involve resource allocation, risk, tolerance, and ultimately, how much we're willing to invest in monitoring and potentially mitigating risks that are probabilistically small but potentially consequential. The challenge is that resources are finite. Telescope time, analysis capability, and funding all have limits. We can't treat every distant comet as if it's an immediate threat. But we also can't ignore objects that are genuinely unusual, because those are exactly the objects most likely to surprise us. C₂-dominated Atlas sits in this uncomfortable middle ground. Interesting enough to warrant attention, unusual enough to generate uncertainty, but distant enough that mobilizing a major observational campaign is hard to justify. Looking forward, what lessons should we take from C₂-dominated Atlas? First, we need better monitoring capabilities. The observational gaps I discussed earlier are not acceptable for objects that might pose even small risks. We need dedicated survey telescopes that can provide continuous coverage, not just intermittent snapshots. Second, we need better models. Our current trajectory prediction tools are excellent for well-understood objects but struggle with outliers. We need models that can handle unusual compositions, complex outgassing patterns, and potential fragmentation more robustly. Third, we need to think beyond impact probability. The debris field scenario, the gravitational stirring effects, the potential long-term influences, these all matter, even if they don't fit neatly into current risk assessment frameworks. Fourth, and perhaps most importantly, we need to be honest about uncertainty. The agencies do excellent work, but there's a tendency in public communication to emphasize certainty. The orbit is well constrained, there's no threat, when the reality is more nuanced. Uncertainty isn't weakness. It's honest acknowledgement of the limits of our knowledge. For C₂-dominated Atlas specifically, the near-term future is fairly clear. It will make its closest approach, we'll observe it as closely as we can, and then it will recede. The immediate danger, such as it is, will pass, but the questions it raises will linger. How accurate were our trajectory predictions? Did we correctly characterize its behavior? Were there effects we missed? And most importantly, what will we do differently when the next unusual comet comes along? Because there will be a next one. The universe is full of small bodies, and statistically we should expect to see more interstellar visitors, more unusual comets, more objects that don't fit our standard templates. C₂-dominated Atlas is a dress rehearsal. It's testing our systems, our models, our communication strategies, and our risk assessment frameworks. And honestly, we're finding gaps. Not catastrophic failures, but areas where we could and should do better. Let me step back from the technical details for a moment and share why this story has consumed so much of my attention. When I first started researching C₂-dominated Atlas, I expected to find either clear evidence of threat or clear evidence of safety. What I found instead was something more unsettling, genuine uncertainty, complicated by unusual object properties, observational gaps, and model limitations. The agencies say there's no threat and they're probably right, but probably is doing a lot of work in that sentence. What bothers me isn't the specific numbers, the distance, the trajectory, the impact probability. Those are all reassuring. What bothers me is the realization of how much we don't know, how many assumptions our models make, how many ways an unusual object could deviate from expectations. We live in an age of remarkable astronomical capabilities. We can detect planets around other stars, image black holes, track objects billions of light years away. And yet, for a comet that's practically in our backyard, we're dealing with significant uncertainties about its composition, structure, behavior, and long-term trajectory. That's not a criticism of scientists. They're doing phenomenal work with the resources available. It's an observation about the inherent difficulty of the problem and the limits of what we can know about small, distant, rapidly changing objects. Throughout history, humanity has grappled with uncertainty in the face of potential threats. Sometimes we've overreacted, seeing danger where none existed. Other times we've been complacent, dismissing warnings until it was too late. The challenge with C₂-24 G3 Atlas is finding the appropriate middle ground, taking the uncertainties seriously without succumbing to fear, maintaining vigilant observation without declaring crisis, and being honest about what we know and don't know. I don't have easy answers. This isn't a story with a neat conclusion where everything's resolved and everyone goes home satisfied. It's a story about living with uncertainty, about doing the best we can with incomplete information, and about preparing for possibilities we hope won't materialize. For those who want to understand the technical details more deeply, let me walk through how trajectory predictions actually work and where the uncertainties creep in. The starting point is astrometry, precise measurements of where the comet appears in the sky at different times. By combining multiple observations taken from different locations and at different times, you can work backwards to deduce the comet's orbital parameters, its semi-major axis, eccentricity, inclination, and so on. If the comet were an inert object moving only under gravitational forces, this would be straightforward. More observations mean better determined parameters, and trajectory predictions would become increasingly reliable. But comets aren't inert. They're venting material, which creates forces that need to be added to the equations of motion. These non-gravitational forces are typically modelled using something called the Marsden parameters, or more sophisticated versions thereof. The basic idea is to add extra acceleration terms to the equations. One component in the radial direction, toward or away from the Sun, one in the transverse direction, perpendicular to the radial direction but in the orbital plane, and one in the normal direction, perpendicular to the orbital plane. The magnitudes of these accelerations are free parameters that get fit to the observational data, along with assumptions about how they scale with distance from the Sun, since outgassing depends on solar heating, which depends on distance. This works reasonably well, but it's a simplified model. Real cometary outgassing is much more complex with multiple active regions, rotation effects, time-varying activity, and so on. The simplified model tries to capture the average behavior, but there's no guarantee it correctly represents what's actually happening. For C₂-24 G3 Atlas, the unusual composition, CO₂-dominated, means the standard distance scaling might not be appropriate. The observational anomalies suggest the outgassing might be more complex than the standard models assume, and the limited observation arc means the fitted parameters have significant uncertainties. All of this feeds into uncertainty in the predicted trajectory. When you project forward weeks or months, those parameter uncertainties grow into positional uncertainties that can span thousands or millions of kilometers. The agencies account for this by providing uncertainty envelopes, basically a range of possible trajectories consistent with the observations. The nominal trajectory, the center line, is the most likely path, but the comet could plausibly be anywhere within the envelope. For C₂-24 G3 Atlas, the published uncertainty envelopes are reassuringly large when it comes to Earth impact. Even the worst-case trajectories within the envelope pass safely. But worst case within the envelope assumes the envelope is complete, that our models are capturing all the relevant physics, that there aren't behaviors or forces we're missing, and this is where the unusual nature of the comet introduces doubt. If the object is doing something our models don't account for, then the actual range of possible trajectories might be larger than the calculated envelope suggests. One of the most difficult aspects of this entire situation is communication. How do you convey appropriate concern about genuine uncertainties without causing panic? How do you explain technical nuance to a general audience? How do you balance reassurance with honesty? The agencies have chosen, understandably, to emphasize reassurance. Their public statements focus on the nominal trajectory, the safe distance, the low impact probability. This is appropriate for preventing panic and maintaining public trust. But there's a cost to this approach. It creates an impression of certainty that may not be fully warranted. When astronomers use phrases like, "the trajectory is well constrained," what they mean is, well constrained given the model assumptions and observations we have. But that nuance often gets lost in translation. The general public hears no threat and assumes zero possibility of danger. Scientists hear no significant probability of impact given current understanding, and know that's a subtly but importantly different statement. I've struggled with this throughout my investigation. How do I present the genuine uncertainties I've uncovered without being accused of fear-mongering? How do I question the standard narrative without appearing to be a conspiracy theorist? How do I advocate for better monitoring and more caution without implying that disaster is imminent? The answer, I think, is to be as precise and honest as possible about what we know, what we don't know, and what the implications are. To acknowledge that the most likely outcome is exactly what the agencies say, a safe, distant passage, while also exploring the edges of possibility. Because that's what responsible risk assessment requires. Looking at the low probability scenarios, understanding their consequences, and deciding whether they warrant additional attention or resources. So where does all this leave us? C₂-24 G3 Atlas is most likely going to pass safely, exactly as predicted. The agencies are probably right. The models are probably adequate. The uncertainties are probably smaller than I've made them sound, but probably isn't certainty. And for an object this unusual, with its strange chemistry, its anomalous observations, its poorly understood behaviour, I believe those uncertainties deserve more attention than they're currently receiving. This isn't about panic. It's about preparedness. It's about honest assessment of what we know and don't know. It's about building better systems for monitoring and responding to unusual objects. It's about expanding our definition of planetary defense to include not just immediate impact threats, but also longer-term influences and low probability, but high-consequence scenarios. C₂-24 G3 Atlas is a teacher, if we're willing to learn. It's showing us the gaps in our observational capabilities, the limitations of our models, the challenges of communicating uncertainty, and the need for more sophisticated approaches to assessing cosmic risk. As it passes through our neighbourhood and continues on its journey, we'll learn more. We'll see whether our predictions were accurate, we'll understand better how this unusual object behaves, and hopefully, we'll take those lessons and apply them to future encounters with objects we haven't even discovered yet. Because the universe is vast and full of small bodies, and sooner or later something genuinely dangerous will head our way. When that happens, I want us to have learned everything we can from benign encounters like this one. I want our monitoring to be comprehensive, our models to be robust, our communication to be clear, and our response capabilities to be ready. C₂-24 G3 Atlas probably won't be the object that tests us, but it's preparing us for the one that will. Stay curious, stay vigilant, and keep watching the skies.